Okay, now we're gonna derive Gauss's law. Okay, so Gauss's law is an alternative to Coulomb's law, as I said. So they're totally equivalent. Okay, so you can think of Gauss's law as a conclusion of Coulomb's law, or you can think of Coulomb's law as a conclusion of Gauss's law. Okay, it's a different way to express the relationship between the electric charge and electric field. Okay, so it's one of the equations in the Maxwell's equations we're going to see at the very end of this class. Okay, so and then it's a relationship between the net electric flux through a closed surface and the net electric charge inside this surface. Okay, so it only applies to closed surface. Okay. So let's see how we can derive Gauss's law. As I said, you can think of Gauss's law as the conclusion of Coulomb's law. So you can derive Gauss's law from Coulomb's law. So that's what we're going to do now. You can do this. Start from this definition of flux, and then let's do that in steps. Let's first calculate the flux, okay, through a sphere, okay, which is centered on a charge, like positive charge, okay? So that's what we want to do first, okay? Then we're going to generalize that. Say I have a positive charge here. Now I'm going to draw a surface, okay? Or I'm going to make a real surface, doesn't matter, okay? The surface doesn't have to be real, right? It can be imaginary, okay? As we're going to see when we solve a problem, usually we use an imaginary Gaussian surface, okay? So there's the surface. Say you put this spherical surface, you put this charge right at the center of this surface, right? You can do that, okay, if you have a real surface. Okay. Now I want to find the electric flux through this surface. Okay, where does this electric flux come from? Well, this guy has the electric field, right? And we know how to draw the electric field created by this positive charge, right? Away radially outward, away from this electric field, electric charge, right? And the magnitude of this electric field is going to be this. Now, if I call this guy Q over R squared, and it's positive, I don't need to absolute value sign. And remember, how did we derive this? This is from Coulomb's law, right? We derived this from Coulomb's law, so that's the electric field created by any point charge at any point around it. Now we're going to use that conclusion and then find the flux through this spherical surface. Okay. Now how do I find the flux through this spherical surface? Remember, this is not a circle. You should imagine it's a three-dimensional spherical surface which has this charge right at the center. Okay. Now let's do that. Let's just use definition, right? This is definition. So I would need to find the electric field, the dA and cosine theta. If there's any constant, right, from our experience, if there's any constant, I can just take them out, which is very nice, right? So in this case, if this is a spherical surface, okay, with the charge right at the center, that means all these distances, they're going to be the same, right? Say this is like a big R. I pick a very special. Now let's just use A. Okay, so that means this at every point, the distance from the center to the surface is going to be the same, A, right? That's why it's a spherical surface, right? So that means the electric field at every point, right? At this point, it's going to be Ke Q over A squared. At this point, Ke Q over A squared. So E will be a constant, right, on this spherical surface because I put this charge right at the center of this spherical surface, okay? Because this is a very special case. So this E, I can take it out. I would only have dA, okay? Now, what about this cosine theta? Remember, the theta angle is the angle between this dA and the E, right? So dA is gonna be, you pick a very small element here, okay? What is the dA? perpendicular, and this is a closed surface outward. So you should draw dA this way. Now at this point, what is the direction, what is the angle between the dA and E? They're in the same direction. It's going to be 0. What about this point? Okay, if I pick a small element here, the dA perpendicular outward. So I should draw dA that way. What is the angle between E and dA? Oh, still 0, because they're still in the same direction. So at every point, right, I pick a small element here, dA, it's going to be down. Now at this point, dA and E in the same direction. Okay? So in this case, the cosine theta is going to be cosine 0 everywhere, because the electric field is perpendicular to the surface everywhere. Okay? In this case, it's not a uniform electric field, not flat surface, but this is a very special case because the electric field is it's radially outward. Okay? So if you make a spherical surface with the charge right at the center, the electric field will be perpendicular to the surface everywhere. So this is a very special case, but it's still perpendicular. Okay? So that's still going to be E. Take this cosine 0 out, because there's a constant everywhere. You get this. Okay? And this is just going to give you A, right? So this is exactly going to be E times A. And even the steps are the same as the flat surface we discussed that when we introduced electric flux, right? So perpendicular doesn't have to be straight lines, uniform with flat surface. Right? In this case, as long as it's perpendicular everywhere, okay, the electric field, the electric flux is going to be E times A, right? Now you see that I can plug in the E and this expression of A, put them together, you can find a flux, right? So now you can pause the video and then put them together, see if you can find. Remember, this A is the area of the sphere. What is the area of the sphere? If you don't remember that, you can Google it, right? But you should have learned that before. Okay? So if you put everything together, this is KE Q over R squared. In this case, it's going to be A squared, right? So I'm going to put an A here. Now, what is the area of this surface? The spherical surface is 4 pi r squared, right? What is the radius of this spherical surface? That's A, okay. But it actually doesn't matter, right? You see that the radius squared, they're going to be canceled, right? So you will get 4 pi Ke Q. So that's going to be my answer, right? And it's a very nice answer because 4 pi Ke constant, they're never going to change. The only thing that changes is Q, right? So this is going to be general conclusion, right? If there is a source charge, point charge, single point charge, and I put this point charge right at the center of the spherical surface, okay, then the electric flux through this surface, it's just going to be 4 pi KEQ. I don't even need to do any integral, right? This is going to be a very nice conclusion, okay? All right, so now let's see. What if I draw a spherical surface smaller or bigger than this? Am I going to get the same conclusion, right? So say if I draw a spherical surface like this, so smaller than that, okay? Or I have a smaller surface. I just put this charge right at the center of that smaller surface and calculate the electric flux through this smaller spherical surface. Again, it's not a circle, it's still a spherical surface, closed, okay, with the charge right at the center. Are you going to get the same answer? You will, right? You're going to repeat all the processes, every step, right? The same process, right? Nothing is going to change. Now you're going to plug in the radius of the spherical surface, the smaller surface. So you're going to plug in a smaller radius here. You will also plug in a smaller radius here, but they're going to cancel always. At the end, you still get this, right? Okay, so the conclusion doesn't depend on the radius of this sphere, right? Even if you draw a larger one, say I draw another surface like this, spherical, still a spherical surface with the charge right at the center. I want you to calculate the flux through the spherical surface, okay? You will still repeat every step. Now you're going to plug in two large radius, right? But it doesn't matter. This guy and this guy, they're going to cancel, right? They still cancel. You still get this, okay? So this is a very nice conclusion. If there's a point charge, you put this point charge right at the center of any spherical surface, right? You don't really need the radius of this spherical surface. If you want to calculate the electric flux through this surface of this spherical surface, you always get this. You always get this, okay? And then you can even carry the sign of this charge, right? If you get a negative charge at the center, so the direction of this electric field lines is going to be inverted, so it's going to be in that direction. So you will get a cosine 180, but that's just going to be included in the sign of the charge, right? So you can just use this as a general conclusion. For any important charge, if there's a spherical surface, okay, with the charge right at the center, the flux, the electric flux through this surface, it's always going to be there, right? Isn't that nice, right? It's a very nice conclusion. And that's only true when Coulomb's law is true, right? This is the conclusion from Coulomb's law. So that when you do all the algebra, you will get this, then the radius squared is going to cancel the radius squared in the area. So you don't have any radius, okay? And this is also true if you use the fact that electric flux is proportional to the number of electric field lines crossing this surface, right? Compare these three surfaces. For every single electric field line, it's going to always pass all of them, right? If this single electric field line passes this one surface, it's going to pass this one. It's going to always pass that one. This line, right? For every single electric field line you draw created by this electric charge at the center, it's always going to cross all these surfaces. Of course, they will have the same number of electric field lines passing them, right? So they will have the same flux. So all you need to do is just count the number of electric field lines through each surface. And in this case, so smaller one, big one, doesn't matter. The number of electric field lines passing through each surface, it's going to be the same. Okay? So of course, they will have the same electric flux. Okay. Now you can even generalize it to an irregular surface. Okay, so now let's use another surface. It's not a spherical, it's just a crazy surface, okay? Like this. Let's make a surface like this. Okay, this is still three-dimensional surface, but it's just crazy surface, right? It's still closed. Three-dimensional surface with the charge right at the center. You can still do this calculation, okay? Well, it's going to be a little bit tricky if you want to prove it rigorously, okay? It's going to be a little bit tricky, but at the end, you will still get that. Okay, I'm not going to do that here, okay? I'm just going to use, again, the fact that the electric flux is proportional to the number of electric field lines, okay, to argue that it will be the same. Take a look at this surface, this crazy surface. If you compare the number of lines passing through this crazy surface with the number of lines passing through any of these spherical surfaces, are they the same? Of course they're going to be the same, right? You draw a single line. This line from this charge, okay, it's going to pass all these surfaces, including this crazy surface. This line, all the surfaces, including the crazy surface. Every single electric field line you draw coming out from this positive charge, or if you have a negative charge, you draw lines going into the negative charge. These lines, they're going to pass every single surface as long as you put this charge inside this surface, right? So the charge has to be inside this surface. And then the surface can be totally crazy. It doesn't matter if it's spherical, rectangular, doesn't matter. As long as it's a closed surface, it's it has this charge inside the surface, right? So it doesn't even have to be at the center, right? You can move the charge around here, 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 here. As long as it's inside this crazy surface. You do this calculation, you always get this, okay? And because if you count the number of lines of these electric field lines passing through every surface, they're all going to be the same. So this is going to be a very nice conclusion, right? If there's a surface, okay, with a charge inside the surface, right, and then you calculate electric flux, okay, you can do that. You can do that. You can do every step very carefully, okay? But I'm going to tell you the answer, it's always going to be this, okay? It's always going to be this because I just proved that, right? So I don't need to do this calculation for every surface with a charge inside the surface. Just tell me the charge, the sign, and the value. I'm going to plug it in. I will always get this, okay? So that's a general conclusion. If you have a charge inside a closed surface, right? Now we can do this, okay? What if we have another case? The charge is outside the surface, okay? So I just argued for all kinds of surfaces. As long as the charge is inside the surface, I always get that value, right? But another case is this, right? If I have a charge here, it's going to have electric field lines, right? Now I can have a surface here. Still crazy, okay? This is a closed surface. This is a closed surface. What if I want to calculate the flux through this surface? Then you cannot use that conclusion because that conclusion we drew it when the charge is inside the surface, right? So in this case, well, you can still do this. You can still use the definition, okay? You can prove it, okay? If you do that very carefully, okay? But again, I can do it in a short way, okay? I can use a shortcut because, as I said, all you need to do is just count the number of lines passing through the surface. And then if this is a closed surface and the charge is outside the surface, you take a look at all these lines passing through the surface, right? If this line passes through the surface, enters the surface this way, it's going to always leave the surface on the other side, right? It's going to enter the surface here, it's going to leave the surface here. And then if you do cosine theta at this point, your dA should be outward. And your dA at that point is going to be outward. And E is the same direction, right? So that means this element and this element, they're going to contribute two numbers in this integral without the signs, right? Because this is going to be a cosine number, right, in positive. This is going to be a cosine angle negative, right? Because this is the electric field, this is dA. You're going to get an angle larger than 90 degrees, right? And then if you take a look at this line, it's going to enter the surface here. It's going to leave the surface on the other side. So again, if you calculate this, you're going to get a dA this way. Okay, you're going to get a dA this way. They will contribute a positive and negative number. Okay, so at the end you can pick every single line. This line, okay, this line has nothing to do with this surface. You don't need to include this, right? So you can draw more lines if you like, right? So for every single line, this one, if it enters the field, if it enters this surface on this side, it's always going to leave the surface on the other side, right? Because this is a closed surface. If it's an open surface, it's not true. But if it's closed surface, right, it's always going to be true. Always going to be true. So you always get a positive number and negative number, positive number and negative number. And they're going to cancel out exactly, okay? At the end, so I'm not going to do the derivation. At the end, you will get a 0, okay? So you can also, again, use the number of lines to understand that. Because when this line enters the leaves, it's going to cancel out, enters and leaves, the contribution, they're going to cancel out, right? So the net number of lines passing through the surface it's going to be 0, right? So the net number of electric field lines passing through the surface is going to be 0, right? This is going to be negative, positive, negative, positive, negative, positive, right? So at the end, you will get a 0. So, and this is going to be a conclusion, general conclusion again, because for any charge outside the closed surface, you draw the electric field lines, okay? These lines, either they don't cross this surface at all, or they will always enter the surface on one side and then exit the surface on the other side. Positive and negative, they always cancel out, exactly. So you always get a 0, okay? So now we have two nice conclusions, right? So if this Q inside a surface, the flux, it's always going to be 4 pi KEQ. If Q is outside a surface, the flux is going to be 0. But the surface has to be closed, right? This doesn't apply to open surface. Now we can generalize this to a combination of charges, right? So now say I have a crazy surface like this, okay? Now I have a bunch of charges here, right? This charge is outside, this charge is inside, this charge is outside, this charge is inside, inside, outside, inside, outside. So each charge is going to have its own electric field, right? So if I want, then there should be a net electric field at every point, right? For example, I want you to calculate electric field at this point. Well, that's going to be hard because you're going to include the contribution from each charge and add all these vectors together, x and y components, right? Vector analysis, right? And you can I want you to calculate electric field here, 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 or a point at the surface, okay? That's going to be crazy, right? So if I want you to use this definition, to find this electric flux, oh, that's going to be very, very hard. That's going to be very hard because the electric field is not uniform, right? You would have to calculate electric field everywhere. And also the surface is not a regular surface, right? So even if you use this, it's going to be a very, very difficult electric integral to evaluate. But I don't need to do that actually, okay? I can just use these two conclusions, right? Because the flux in this through this surface from the electric field created by all these charges, right? I can still do that. The electric field mathematically is going to be electric field total created by all these charges. But that's just going to give me E1 plus E2. So this is totally math, okay? Totally abstract. Dot dA, right? So that's what I would do mathematically. Now I can distribute it, right? When I distribute it, I will get this. E1 dot dA, that's the first term. E2 dot dA, that's the second term. E3 dot dA, okay, dot, dot, dot. But then you see that this guy is just going to be the electric field created by the first charge, right, through the surface. So that's pretty much that, say this is Q1. I just need to calculate the contribution from Q1. And then I can use this conclusion, right? Because Q1 is outside the surface, so this term is going to be 0. Okay? Look at this term. This is just going to be, you remove all the other charges. You only have Q1 here. You calculate the electric field from Q1 through this surface, right? If it's outside, you get a 0. Now Q2, if I call this guy Q2, well, this term is just going to be when you have a charge inside the surface. You only have Q2 here, you move all the other charges, this is the term you're going to get. And for this Q2, I can just use this conclusion. So I will just get 4 pi Ke Q2, right? So if Q3 is outside, it's 0. If Q4 is inside, 4 pi Ke Q. So that means if I do it this way, after I distribute it, okay, what do I get? I will get a very nice conclusion. So the total flux through that surface is just going to be 4 pi Ke, and then I'm just going to add all these charges together inside the surface, right? So Q2 inside, Q4 inside, like this 4. So all I need to do, if this is the case, I add all these 4 charges together, right? Everything else, forget about them, right? Because they're going to give me zeros, right? So at the end, I will just get all the charges inside added together with the signs, right? So you don't drop the signs, right? You keep the signs. All right, so and then at the end you will just get this, okay? So it's very nice. So all you need to do is just do 4 pi Ke and then add all these charges inside the surface together, put them here. That's it. Instead of finding the electric field and then integrate that on the surface, which is going to be super hard, right? So this is a very nice conclusion, okay? This is going to make the calculations of electric charge, electric flux through any closed surface much easier than evaluating this integral directly, okay? And then if you remember that there's a relation between this Ke and this epsilon naught, right? Ke equals 1 over 4 pi epsilon naught. So using that conclusion, you can actually write this equation in a nicer way. So as physicists, we always want to write equations in a nicer way. Okay, so instead of writing 4 pi Ke, let's just write an epsilon naught at the bottom, right? Even though they're the same. Okay, so that's going to be Gauss's law. Okay, so take a look at the summary in slide 11. The net electric flux through a closed surface, it has to be a closed surface, right? If it's open surface, then you can't do it this way. You still have to evaluate the integral. The electric flux through a closed surface is always going to be equal to this. So it's very easy to calculate, right? You don't really need to do it the hard way. You just count how many charges are inside this surface. Okay, add all these charges together. Divide them by this constant, then that's it. Okay, so that's the Gauss's law. Okay, and sometimes we write it this way because it's a closed surface. Okay, we write the integral sign with a circle on it. Okay, to imply this is a closed surface. So this is the definition of the flux, right, on any closed surface. This is very hard to calculate, very hard, right? If you have many charges, right? But Gauss's law tells us, okay, you don't have to do that. Add all the charges together inside this closed surface, and then divide that by the constant. That's going to be the value, okay? You just do algebra, so it's very easy, okay? So what's the use of Gauss's law? We can use Gauss's law, okay? So first of all, as I said, Gauss's law is an alternative of Coulomb's law. So you can think of it's a conclusion of Coulomb's law. But actually, in advanced ENM theory, we think of Gauss's law is actually the fundamental theory. Okay, even though it's not that intuitive, right? It doesn't have any force or charge, right? Well, it does have charge, right? Okay, but that's a fundamental theory in nature, and Coulomb's law is just a conclusion of this law. And you can see that using Gauss's law, we will be able to unify electric field and magnetic field. So that's a significance of Gauss's law. Okay, it's very important. Okay, that's the meaning of Gauss's law. So practically, it doesn't really, it's not that useful. Okay, but we can still use that to find the electric field when there's a very good symmetry, okay, of a continuous charge distribution, because we know that finding the electric field from a continuous charge distribution, it's always hard, right? We have done that before, right? You have to evaluate the integral. There's no way you can avoid that, right? It's going to be hard. And it was one of the hardest part, as I said, right? But using Gauss's law, okay, if there's a very good symmetry in this charge distribution, okay, so sometimes using Gauss's law is going to make the calculations easier, okay, So that's what we're going to do. We're going to practice Gauss's law in this part. That's the thing we're going to do with Gauss's law in this part. Okay, we're going to see Gauss's law at the very end of this class, so that we can see that it unifies the electric field and the magnetic field. But for this part, we're just going to use Gauss's law to still calculate the electric field from some very symmetric charge distribution. Okay. So how do I use this law to find the electric field? Okay, so there are some general steps. So take a look at the steps on slide 12. You don't need to memorize these steps, right? You just practice them, so you will understand them. Okay. So in order to use Gauss's law, you need to have a closed surface. Okay. Sometimes there will be a closed surface in the problem. Okay. Sometimes there isn't. So you can draw an imaginary surface, right? So it doesn't have to be a real surface. You can draw an imaginary surface for you to help you calculate the electric field, okay? So we call that surface Gaussian surface. So it doesn't have to be a real surface in the problem, okay? It can be totally imaginary. It's a mathematical tool we use to help us calculate electric field. Then we're going to evaluate this flux using two different ways, right? This is the definition. This is Gauss's law, okay? Gauss's law is very easy, right? You just count how many charge are inside this Gaussian surface. But if you have a continuous charge distribution, this Q in can be tricky, okay? Sometimes you need to calculate this Q in, right? You don't have things to add, right? Because it's a continuous charge distribution. So that's what you do on the right-hand side. You find Q in, right? Epsilon naught is a constant. Now this E dot dA, you're going to still use the definition, use the integral to calculate the E times A. So you will have the electric field on the left-hand side, right? Then you rearrange this equation. You will find the expression for the electric field. Don't forget what we're doing. We're using Gauss's law to help us to evaluate the electric field from some very symmetric charge distribution. Our goal is still to find the electric field, okay? So, but again, on the left-hand side, in this part, we never need to evaluate the integral. It's always going to be these special cases we have seen. Perpendicular, E times A. Parallel, 0. And then if there's an angle, then there will be EA times cosine theta. Okay? So, don't be afraid of the left-hand side, right? You never need to evaluate any integral in this part with Gauss's law in electric flux. You never need to do that, okay? So it's easier than the one with the electric field calculating using superposition principle, okay? But still, this is very abstract, okay? This is very abstract. You still need to do a lot of work in this part, do a lot of practice so you get used to it, okay? Now let's take a look at some examples. Okay, so we see, we know how to use this Gauss's law to help us find the electric field from some continuous charge distribution. So let's start with a solid sphere, uniform charged. Okay. So we're going to find the electric field created by a solid sphere, okay, using Gauss's law. Okay, so what is Gauss's law? I'm going to rewrite it here. Right. If there's a closed surface in the electric field, the flux is always going to be equal to the charge inside the closed surface divided by the constant. Okay. Now say there's a solid sphere, uniformly charged, positive, say. Now I want a sphere, not a circle, okay? Should imagine it's a sphere, okay? Now the sphere has a total charge Q, and then has a radius R, big R, okay? Now we want to find the electric field at a point outside the sphere. So say I want to find the electric field at this point. How do I find the electric field? Well, you can use superposition principle, right? If I want to use superposition principle, how do I find the electric field? Well, I would do this, right? Pick this charge and draw the electric field at this point. That's going to be away from it, right? And then pick another one. There's a charge here, and this charge is going to have an electric field in that direction. And then, okay, I realized that these two electric fields, they're going to cancel Y components, right? Only X components left. So that symmetry is going to help me. So the net electric field at the end is going to be in that direction, right? So at the end, the net electric field is going to be in that direction for sure, okay? So I only need to worry about the X direction. So the net electric field is only going to have X component, right? Doesn't have any Y component in this problem. So how do I find this net electric field in X component? Well, I will do this, right? Integrate this X component of this dE. So now you're going to call every single one dQ. You're going to find the expression for dEx, right? So pretty much by doing dE times cosine or sine, something like that. And then you're going to find a way to write everything in terms of one variable, okay? You can find that variable, and then at the end look it up in the integral table, and then find that, right? That's how you would do that using the superposition principle, using the theory we learned before. Now we want to use Gauss's law to do that, right? So instead of using this, if I use Gauss's law, first of all, the direction is still going to be that, right? So that's easy, okay? I already know the direction, okay? Even without doing any calculations from the symmetry of the problem, right? So I know that the electric field at this point must be in that direction, because for every single charge I pick, right, I can always find another one, okay, which pairs with it, pairs up with it, and then it's going to cancel the component perpendicular to that one, right? So it doesn't have to be those two ones, right? You can pick any two little elements. They're always going to cancel the components perpendicular to this axis. Right? So it doesn't have to be straight up and straight down, right? You can pick two charges, which is going to have a component in this way and this way. They're going to cancel out, right? But anyway, the net electric field is going to be in that direction because all these perpendicular components, they're going to cancel out because this is a spherical, this is symmetric, solid sphere, okay? So the electric field is going to be in that direction. Okay, easy. Now, what about if I want to find the magnitude of the electric field at this point? So I don't want to use superposition principle, right? Because I don't want to do that integral, right? I want to use Gauss's law. If I want to use Gauss's law, I would want to draw a surface, use a surface, okay? So, and then I can apply this law and find the charge on the right and then do the integral on the left. And then if I want to evaluate this integral, right, I don't really want to integrate anything, right? I want everything to be constant, right? So as possible as I can. If I can find everything to be constant, like E is a constant, cosine theta is constant, I take them out, so the left-hand side is not going to be an integral anymore, right? So I would want to find a surface. First of all, I would want the electric field to be constant so I can take it out, right? I don't want to have the electric field inside the integral, right? So in this case, if I want to draw a surface, right, find a surface, okay, to help me figure out the electric field at this point, and then I also want the surface to have all these electric fields with the same magnitude, right? How would I draw the surface? Well, I know that, let's take a look at this point and a point here, which has the same distance to the center. So if I ask you, what's the difference between these 2 points? Well, the only difference is that the electric field at this point is going to be to that direction, right? But they should have the same magnitude. Why? These 2 points, they're totally equivalent, right? What's the difference between them? There's no difference between them, right? If this guy is radiated out with the same number, like 5 newtons per coulomb, this should be 5 newtons per coulomb in that direction, right? So if I pick another point here, What is the direction? Well, again, you would say, oh, that's easy because I figured out this. Electric field at this point is going to be straight down, right? Because they are totally equivalent, right? If this is a straight outward, this is straight outward. If this is 5 newtons per coulomb, this must be 5 newtons per coulomb, right? Because to this sphere, there's no difference between these 2 points. It's totally symmetric. So, okay. And that point, if I draw a point there, that's going to be straight up. Right? So what if I connect all these points together, right? So I don't only have these 4 points. If I connect all these points, which has the same distance to this center, right? They should all be equivalent, right? For example, if I pick a point here, what's the difference between this point and this point and this point? There's no difference, right? They're totally equivalent. What about a point here, a point here? So if you connect all these points, you want to put all these points on a surface. What is a surface you would draw? You draw a sphere, right? You draw a spherical surface. Okay, which has all these points on it, okay? Okay, this doesn't look like a sphere, but you know what I mean, okay? All right? So that's the Gaussian surface I'm going to use to help me calculate the electric field, because I want to make the integral as possible, as easy as possible, right? So if I remember, this is a Gaussian surface. This Gaussian surface is a spherical surface, okay? So it's not a circle, okay? It's a 3-dimensional spherical surface. Imagine it's a spherical surface, bigger than the real surface. This is a real solid sphere. This guy has a charge on it. This is an imaginary surface. This guy doesn't exist. It's a mathematical tool I drew to help me find the electric field I want. It doesn't exist, okay? But if I use this surface, right, then all the points I pick on this surface is going to have the same E. So if I apply this law on this surface, Gaussian on this surface, so I can take this E out on the left-hand side. So that's the point. I draw a Gaussian surface. Okay? So now let's do that. Okay? I decided I'm just going to draw still a spherical surface with all these points on it. With this point, the point I want to find, right? And all the other points on it which has the same magnitude of electric field, so that I can take this E out. Now let's see. Now I'm going to apply Gauss's rule. So on the left-hand side, I would have E dA cosine theta, right? On the right-hand side is going to be Q in over epsilon naught. Now I'm going to work on the left and right-hand side, okay? The left-hand side is going to be E. I just figured that E is going to be the same everywhere, right? At this point, E is going to be radiated out, because it's totally equivalent. All these points are totally equivalent, right? If you rotate this point a little bit, it becomes this point. So it's going to be in that direction, okay? So the E direction is going to be always radiated outward, and the magnitude is going to be the same, so I can take it out, right? Now, what about the angle theta, okay? How do you find angle theta? Angle theta, it's always going to be the angle between this dA and the E. I already figured out the E is going to be in that direction. What is the direction of dA at that point? If this is a surface closed, I pick a very small unit here, very small element here. This is going to be how I draw dA. What is the direction between them? 0, right? What about this point? I pick a very small element here on the very bottom of this spherical surface. What is the direction of dA? Down. Right? So, okay, now I see the patterns. For every point, the dA is always going to be perpendicular to the surface. And because the electric field is outward, so the dA is always going to be the same direction with this electric field. So this is pretty much like the point charge we saw, right? The only difference is that now it's a solid sphere, but it's not a point charge, right? But the electric field and dA, they still make a 0 angle, okay, 0 degree angle. And it's always the same. So I would get cosine 0 here and dA. Okay? Now this is just going to be E times A. Because cosine 0 is 1. You integrate this dA, you get A, right? So there's no difference. Now, the right hand side, it's going to be Q in, right? So what is a Q in? The charge inside the Gaussian surface you draw. This big surface is the Gaussian surface I drew. So whatever charge this guy has, if the problem tells me it's Q, that charge is totally inside the Gaussian surface I drew, right? So I can just use this Q from the problem. But it's not always going to be the Q in from the problem, right? We're going to see a different example. So in this case, you see that that's going to be the equation I set up at the end, right? So how do I find E? Don't forget what we're doing. We're still trying to find the expression for the electric field. Okay? So for this E, I divided both sides by the A. So it's going to be Q over epsilon A. Okay. Then what is the A? A is the area of this big sphere, this solid, spherical sphere joule, right? So how do I calculate the area of this spherical surface? That's going to be 4 pi r squared, right? So, okay, then what is the radius of this sphere? It's not the big R, because I'm not using this surface, okay? I'm using the surface I drew, totally imaginary, which has this point on it. So whatever this distance is, that's going to be the radius, right? So if you tell me this is a little r, so that's going to be 4 pi little r squared. It's not going to be bigger. Okay? So this is something people are going to confuse, right? Sometimes you use big R, little r. If you don't like this little r, you can just use d, right? If you like. Okay? If I call the distance d, the distance from the center to the point I want to evaluate d, I'm just going to use d squared. Or if you want to call it a, just use a squared, right? But it has nothing to do with the radius of the real solid sphere, because I'm not using the surface of this solid sphere to calculate the electric field. I'm using this big imaginary surface which has a radius which is equal to the distance from the center of the sphere to this point I want to evaluate as a radius, okay? So I should always use that distance, okay? Whatever you call it, that's fine, okay? So that's going to be the conclusion, right? So if you ask me, what is the electric field at this point? Outside the sphere, solid sphere. Well, direction, radius outward, and magnitude is going to be that, okay? And then if you realize that Ke equals 1 over 4 pi epsilon r, so you can also write this in terms of Ke q over d squared, or Ke q over r squared. It doesn't matter which symbol you use. You like to call this distance r, d, a, b, doesn't matter. Okay? And this is exactly the same equation for a point charge. So that means the electric field of any point outside the solid sphere, it's going to be equivalent to the electric field of a point charge at the center, right? Which is intuitive, right? Because of symmetry, okay? The effect of this total solid sphere is going to be equivalent to the effect of a point charge Q right at the center, okay? From the symmetry, okay? So that's the electric field created by this solid sphere outside the sphere, okay? So it's very similar to a point charge, right? Actually, it's the same as a point charge, right? Even the steps are the same. Now we're going to move on to a point inside the sphere, okay? So that's going to be a little bit different. So now I'm going to redraw this sphere. And then I want to find the electric field inside the sphere this time, okay? So I'm going to draw the sphere. So that's still a solid sphere. I'm going to draw a little bit bigger because I want to find the electric field at the point inside, right? So this guy has a lot of charge on it. This is the, and then it still has the radius big R, okay, it still carries a total charge big Q, okay. Now I want to find the electric field, say, at this point, okay. At this point, so, okay, how do I find the electric field at this point? Again, if you want to use superposition principle, you would do this. So, pick this charge. This charge has an electric field at this point, in that direction. Pick this charge. This charge has an electric field in that direction. They cancel Y components, only X components in the left. You can pick this guy and this guy, pair it up with this guy. So they will have two electric field in this way and that way. So again, Y components cancel, X components left, right? So the direction is easy. I can figure it out using the symmetry without doing any algebra calculus. So still the electric field, that electric field is going to be in that direction, right? So at the end, I will still get the electric field at this point, the net electric field at this point, in this direction. So outward, okay, radiated outward because this is positive sphere, solid sphere. Now, what about the magnitude, right? Okay, if you still want to use superposition principle, you're going to still do that, right? You're going to do this equals, and you find the expression for dx, and then do this integral, do it the hard way, right? Now, we don't want to do that. We still want to use Gauss's law. We don't remember what we did. We didn't really integrate anything, right? We didn't integrate anything. It's still going to be, it's still the special case when electric field is perpendicular to the sphere everywhere, right? See that? Electric field is perpendicular to the sphere surface everywhere. I get EA on the left-hand side, right? So that's easier than using the superposition principle. So I want to do the same thing here. So again, I'm going to use, so I don't want to do this. I want to use Gauss's law. The flux E dot dA is going to be equal to Q in over epsilon naught. Okay. So I still need to draw a Gaussian surface, right? It doesn't have to be a real surface, can be totally imaginary. I just want to make sure I pick a Gaussian surface where I can find a lot of constants there so I can take them out, okay? So I don't need to integrate anything here. So from the first part, I know that the best surface I can draw is gonna be a spherical surface, okay? So I would draw, so because this is a center, so this point, this point, this point, they will all have the same magnitude, right? The electric field is going to all have the same magnitude. So this is going to be my Gaussian surface. This smaller one is my Gaussian surface. So I'm going to work on this Gaussian surface, okay? So I know that the electric field at any point is going to be radiated outward for sure, right? Because all these points, they are equivalent, right? What's the difference between this point and this point? There's no difference. What's the point of this between this point and this point? There's no difference, right? So they must have the same magnitude, and the direction should always be outward. If this is outward, this is outward, this is outward, okay? So now I'm going to work on this. This is my Gaussian surface, okay? Still an imaginary surface, doesn't exist, totally mathematical concept, okay? Now let's do the left-hand side. It's going to be exactly the same process, right? E dA cosine theta, no change. E is going to be a constant everywhere. That's why I picked the spherical surface as my Gaussian surface, right? So the E is going to have the same magnitude at every point. And then the cosine theta is also going to be cosine 0, right? Because what is the direction of dA at this point? Perpendicular. What is the direction of dA at this point? Perpendicular. What is the direction of dA at this point? Perpendicular. Okay? So dA and E, they still have 0-degree angle. They're still in the same direction. So I'm going to still, nothing has changed on the left-hand side. I'm going to still get E times A on the left-hand side. And this also agrees with one of the special cases we discussed at the very beginning, right? If the electric field perpendicular to the surface everywhere, it's always going to be E times A, the flux, right? Electric field, electric field, electric field, electric field, perpendicular to this Gaussian surface I drew. It's always going to be E times A at the end. Always. The steps are going to be exactly the same, right? All right? So you see that everything is going to be the same up to this point. So am I going to get the same answer? No. Because this Q in, it's going to be different. This Q in is going to be different. Why? Because the Q in is the charge inside the Gaussian surface you drew, okay? What is the Gaussian surface I drew here? This is the Gaussian surface. So you can, if you apply this Gauss's law on this Gaussian surface I drew, because I want to find the electric field at this point, so I have to draw a Gaussian surface which has this point on it, right? I can't draw a Gaussian surface here or bigger, because that point is not going to be in my Gaussian surface. What am I doing, right? I want to draw a Gaussian surface which has this point on it. I have to draw a smaller one inside this real solid surface. How do you calculate charge on this guy, the smaller surface? That's the tricky part, right? I only know this guy, the big solid sphere, okay, this is a big sphere, solid, has a total charge Q. But I only need the charge in this very small portion on this sphere. How do you find that, right? That's what I want you to figure out so we can move on, okay? So that's the question on slide 18. How do you find the charge on this small imaginary Gaussian surface, inside the Gaussian surface? That's going to be the charge you put in here, okay? So in this case, you would use the charge density, volume charge density we defined before to do that, because this Q in is going to be the volume charge density times its volume. Okay? And then how do you find the charge density? The charge density is uniform everywhere, right? So the charge density is just going to be the total charge divided by the total volume, right? That's what it means by charge density, right? So this charge density is going to be the total Q divided by the total volume. Now times the volume inside the Gaussian surface, okay? Now what is the total charge? That's the big Q in the problem. What is the total volume? That's the volume of this solid sphere, right? The total volume. Right? What is the volume of the small sphere? That's the equation for volume. Okay? Now, what is the radius of this guy? Well, it's totally arbitrary. The problem can tell you, let's call this guy little r. Or let's call this guy D, A, okay? B, it doesn't matter, okay? But that's going to be the radius of this small sphere, right? Which, with the radius equal to the distance between the center of the sphere to the point you want to evaluate. So let's call it little r, or whatever you like, the symbol, okay? So now you see that the Q in is going to be Q over r cubed, the big radius, the real radius, times the Gaussian surface you draw, which is actually the distance from the center to the point, okay? That's the Q in. Now you can plug it in and then find the electric field, right? So the electric field is going to be Q in over epsilon A naught times A, right? Now, how do I find that, okay? So Q in, I already have the Q times R cubed over big R cubed. Now, the area is the area of the Gaussian surface, right? We're doing everything on this Gaussian surface, don't forget. We're not doing anything on the real surface of the solid sphere. We are not. We're doing everything on this totally imaginary surface, Gaussian surface. So the area is going to be 4 pi, which r? Little r, if you call the distance r. Or if you want to call it d, a, b, doesn't matter, okay? A lot of books just use little r, okay? Now you can make it a little bit simpler, okay? By canceling things out. So at the end, you would get q. So this r squared is going to cancel 2 powers of this. You have a little r at the top. And then it's going to be 4 pi epsilon naught times r cubed, right? So that's going to be the final answer, okay? And again, if you want to write it in terms of ke, where you just replace this 4 pi 1 over 4 pi e, it's going to be ke, right? But anyway, our conclusion is going to be this, right? So if I put everything together, the direction of the electric field is always going to be outward. Doesn't matter if you pick a point outside or inside the sphere. But the electric field magnitude, so outside the sphere is what we just found, right? It's going to be q over 4 pi epsilon naught r squared, which the r is the distance from the center of the sphere to the point you want to evaluate. So I can just write r greater than the radius, right? What about the any point inside the sphere? Well, that's what we just got. Okay? So they actually behave differently, right? Inside the sphere, you see q is a constant, 4 pi epsilon naught r cubed constant, so it's going to increase with the r, okay? So if you make a plot, okay, if you make a plot, the electric field, magnitude of the electric field with the versus the distance from the center of the solid sphere, right? Initially, it's going to increase linearly. Once it reaches the radius, the outer edge of this sphere, now it's going to decrease with r squared and to infinity. Okay? So that's going to be the plot of the electric field created by the solid sphere at any point, right, inside or outside the sphere. Okay, so that's going to be our complete conclusion. We use the Gauss's law. Okay, it's easier than the superposition principle. We don't need to evaluate any integral, but actually the trickiest thing is the charge inside the sphere, right? It's not always the charge given in the problem, okay? Sometimes it is, sometimes it's not. You have to use the definition of this Q in to find the charge inside the Gaussian surface, sometimes imaginary, okay? To find that charge, find the expression, and then put that in the Gauss's law, and rearrange that, find the electric field. Okay, that's what we're doing in this part with Gauss's law. Still all symbols, still all math, okay? So still a little bit abstract, so you do need to practice a lot so that get used to this new law, okay? I'm gonna stop here for this video.